So we're going to start talking about limits and continuity. And as I mentioned, this is now, the real actual calculus part that we're starting on. Okay? And a limit is what basically sets calculus apart from everything else. Okay? It's that concept of a limit. It sets calculus apart from all the classes that you've had before, because now when we talk about limits, numbers are not just discrete numbers now. We see them as like this continuous array, and where like between 1 and 2 you have an infinite number of numbers. Okay, so what we're going to do first is we're going to talk about rate of change. Now, rate of change is basically how quickly something changes, right? So rate of change is how quickly something changes. When you're driving and your speed is changing from, let's say, 0 to 10 to 20 to 40 to 60, your speed is changing. Now, how quickly that is changing, so how quickly you can see the change on your speedometer, that's rate of change. Okay? Now, let's talk about average speed. You talk about speed ever since, you were very little, and you learned speed in science and then in math and so on. So how do we define average speed? We define average speed as the total distance covered, okay, divided by the total time. So you drive 300 miles and it takes you 4 hours to do it, right? 300 divided by 4, that's on average how fast you were going, all right? So average speed is found by dividing the distance covered by the time that it took you to cover that distance. Since we're dividing distance by time, the units are length per unit of time. So for example, miles per hour, feet per second, centimeters per second, and so on. So now, when I talk about that, when I talk about how much distance I've covered, one way to define how much distance you've covered is to look at where you started and where you ended up. So for example, if you started at 0 feet and you're now at 300 feet, how much distance have you covered? 300, because you did 300 minus 0. Okay? So average speed is the distance covered then, and we say that it's f of t2 minus f of t1. And what does that mean? F of t2 is where you were at your final time, t2. So this is your end position. At t1, the beginning, you were at f of t1. That's your starting position. Okay? So average speed is f of t2 minus f of t1 over t2 minus t1. Over the time interval, t1 and t2, the brackets didn't show up here for some reason. Okay? You have brackets on yours, right? Yeah. Okay. So here, t1 and t2 are the starting time and the ending time. Okay? All right. So take a look at this. An object is dropped from rest from the top of a tall building, and it falls y equals 16 t squared feet during the first t seconds. So this is the number of feet that it falls, so that's the distance, okay? So if it's y equals 16t squared, it's what we were defining before as f of t. So one other way to write y is f of t is equal to 16t squared. So now I have a function. I'm not explicitly told it started from 0 feet and ended at 50, or it started at 50 feet and ended at 0 feet. I'm given a function with which I can find out where it was at T1 and where it was at T2. Okay? So it says during the first T seconds, and now it says find the average speed during the first 2 seconds of fall. So your initial time is T equals 0, and your final time is T equals what? 2. Right. So T1 is 0, T2 is 2. So now delta Y is f of T2 minus f of T1. So basically it's f of 2 minus f of 0 over 2 minus 0. Okay, now f of 2 is 16 times 2 squared. Okay? I'm just plugging 2 into f of t. Yeah.
Why did you use 2 for t when?
Because I'm asked what happens in the first 2 seconds of fall. So in the first 2 seconds of fall, I'm going from time equals what to what? I'm going from time equals 0 to time equals 2 seconds.
And why did you plug in 2 then for the distance?
Well, because what is average speed? Final distance minus initial distance. I'm now looking for final distance, and then I'm going to do minus initial distance. Okay, so let's do that too. So 16 minus 2 squared minus, so that's final distance, minus the initial distance is 16 times 0 squared, all over 2. So that's going to be 64 over 2, which is 32. Okay? So in all, I covered, I have an average speed of 32 feet per second. Yes. Find the speed of the object at t equals 2 seconds and confirm algebraically. So this one here, the formatting got a little off, but basically, let's move on to this next part. Right, my formatting got a little bit off here. So here, calculate the average speed of the rock over the interval from t equals 2 to any slightly later time, t equals 2 plus 8. So now I'm moving on to a different part of the same problem. Here we found the average speed from t equals 0 to 2. Okay? 2 whole seconds. You'll find that in calculus, like that is an infinite amount, an infinite length of time. Here, how about we find it in, let's find the speed from t equals 2 to some later time, 2 plus h. Okay? And that could be like from 2 to 2.5, from 2 to 2.1, from 2 to 4.2. Okay? So let's do that. Let's just be a little bit more specific here, more general here. So how are we going to do this? We're going to do f of t, right. So now we're going to go from t equals 2 to t equals 2 plus h, right? So t equals 2 is my t1. t2, my final time is 2 plus h. Okay? So my starting time is 2 seconds. My ending time is like 2.4, 2.7, 2 plus h. All right. So here, we're going to do f of t2, which is f of 2 plus h, minus f of t1, which is f of 2, over 2 plus h minus 2. Okay, does that look familiar, pre-calc people? People from pre-calc last year? Yeah.
So the top is always going to be the same as the bottom when you first started out. With the exception of the average.
Correct. Right. This is the initial, this is the final position, this is the final time. Initial position, initial time.
So they're always going to be the same. Like, okay.
Yeah, they have to be consistent, not that they're consistent, right? Otherwise you get a negative mistake. Okay, so now f of 2 plus h. What was f of t? 16t squared. So now, what is f of t plus h? It's 16, 2 plus h squared. Does that make sense? Right? So f of t is 16t squared. F of 2 plus h is 16 times 2 plus h squared. Minus f of 2. How much is f of 2? 16 times 2 squared. Right? Over, I have 2 plus h minus 2 is just 2. Okay? All right, so it's h. So let's do this. Let's distribute the top there. So we have 16. Now, I have 2 plus h quantity squared. So it's going to be 4 plus 4h plus h squared minus 16 times 4, which is going to be 64, all over h. Let's distribute the 16. So that's going to be 64 plus 64h plus 16h squared minus 64 all over h. Looking familiar? Yes. Well, you know, you're in the right class to hate it. Huh? Right, because we haven't gotten there yet. Yeah. Huh? Yeah? Huh? Oh, yeah, sorry. Okay. A little bit more?
Yeah, sorry, I'm blind.
Okay.
Thank you, that's good.
Uh-huh.
Okay, so like what exactly is F? Like in every problem that we do, like what is F?
F is going to be given to you. So in this case, you were given a function of the distance, a function of the position. So when the rock falls, the position is defined as 16t squared. F is your position in this case. In other times, it'll be something else. But it's what you're finding the rate of. Okay? You're finding the rate of F. Yeah.
And then just to clarify, this is the average rate that we're finding.
Correct. So we're gonna factor out an h, and we're gonna have 64 plus 16h all over h. Okay. Now we cancel the h's, and the only reason why, so a little bit of deeper math here. We've never really told you guys this, but in order to be able to cancel the h's, it has to be that h is not 0. If h is 0, this whole thing is a faulty problem. But h is not 0, right? Because we're going from 2 to 2 plus h to a later time. Like if we're going from t equals 2 to t equals 2, if h was 0, the whole thing would just be messed up. Okay? So it's fine. I mean, and when you're talking about time, it's not, but yeah. Okay, so we can cancel the h's. Now, what do I have here? 64 plus 16h feet per second. 16h plus 64 will work too. So we gotta have units, even when it's not a pure number. Okay? You will find that the higher up you go in math or physics, the less and less numbers you will have, the more and more variables you will have. Okay? So 64 plus 16h stands for speed. It's got to have a unit of speed. Okay. Important stuff coming up now. No. Okay. Okay. With this, we're calculating the speed from time equals 2 to 2 plus h. The way we're doing it, h can't be 0, so we wouldn't be able to calculate speed at t equals 2. Okay? Because h can never be 0. If h was 0, right? And which means we were calculating the speed at exactly t equals 2. If h was 0, I would have h over there, and I would have 0 over 0, which is not defined. So in order to be able to do this entire process, the big deal is that h can never be 0, but we can bring h as close to 0 as we possibly can. So now, here's the reasoning behind it. I'm looking at the average speed between 2 and 2 plus h. Okay? So for example, between 2 and 3. Okay? That's the average speed. Well, what if I looked at the speed between 2 and 2.1? That's even closer to 2. So if I were to find the average speed between 2 and 2.1 seconds, isn't that pretty much like finding the speed at t equals 2, right? What if I were to find the average speed between 2 and 2.01? That's pretty much like finding the speed at 2. I can make it even closer, between 2 and 2.001. Okay? So I can make that value h closer and closer and closer and closer to 0. And then I could really find the speed at at 2. Okay? So here, the length of time, h, I can make it increasingly smaller. Okay? So if we were to use our expression for speed that we found, depending on the values for h, right? If h is 1, I get a value of 80 for the speed. But if h is 0.1, now I'm even closer to t equals 2, I get a different value, 65. And as I bring h closer and closer to 0, I get closer and closer to t equals 2, and my value is like the most precise for the speed at t equals 2. That's what we were solving before. I'm still continuing the same problem in the previous.
65 to 64.
Right, so if you put in varying values of h into 64 plus 16h, you'll get those more precise values. Okay, so what do we notice here? As h is approaching 0, right, the speed is approaching 64 feet per second. Okay, so by doing that, by taking 2 to 2 plus h, and by making h smaller and smaller and smaller, we could really zero in on the exact speed at t equals 2. Okay? So now we get to the definition of a limit, and here is where we throw all of these Greek symbols at you. Okay? Bear with me, and I'll tell you in words, in English, what this means. Assume f is a function, right, that's defined, and c is a point and on the x-axis, and close to that point, f of x is defined. Okay? Now, x minus c, right? Take a look at x minus c. X minus c is basically the distance between x and another number. As x minus c gets smaller and smaller, we get closer and closer to a limit. That's what that means. So as on the x-axis, as we get closer and closer to c, we get closer and closer to the value of a limit. Okay? That's what that is. So as we get close to an x value, okay, y, the function gets closer to a y value. Okay? Now, here's how the limit is written. So the limit of f of x as x approaches c is equal to L. What this is as x is approaching c, what value vertically is your function approaching? Okay? All right, so let's consider the limit as x equals 0 of sine x over x. So let's graph sine x over x. Sine x over x. I'm going to do zoom 7 for trig zoom. And I'm also going to put my calculator in radian mode. I had it switched for another problem earlier. We're mostly going to be working in radian. Okay, so take a look at this. Now, this is the graph of sine of x over x. As x is approaching 0, what y value is y approaching? What value is y approaching? So basically, as I'm getting closer and closer, to 0, okay, what value vertically is the graph approaching? 1. Okay, so we say the limit of this function as x approaches 0 is equal to 1. Okay, now it turns out sine x over x is like a pretty important function. Okay, so the limit as x equals 0 of sine x over x is equal to 1. Now, it's such an important function that guess what? It'll do you a lot of good if you memorize it. So, if you're walking down the street and somebody taps you on the shoulder and says, hey, what's the limit of sine x over x as x approaches 0? Immediately, it's a 1. Okay? It's going to come in very, very handy throughout the year. All right. So, let's talk about limits for a little bit. Okay. So, let's take a look at, different functions. And let's look at Let's look at the limits as x approaches 1. Okay? So let's take a look at this first one, the limit as x approaches 1. If I'm walking along the x-axis and as I'm approaching 1, right, I look up at the graph, what value vertically is the graph approaching? 2. If I'm approaching 1 from the other side now, what value is the graph approaching? 2. If it's approaching 2 from the left side and 2 from the right side, then the limit is equal to 2. Now, did it actually get to 2? No, that's irrelevant. Okay, that's irrelevant. The limit will still be 2. Here, take a look at this one. As I'm approaching 1 from the left side, the y value is approaching 2. As I'm approaching x from the right side, the y value is approaching 2. Did it ever get to 2? No. Now, there seems to be another part of the graph there, irrelevant for the limit. We don't care. Has no effect on the limit. The limit here is 2. This has no effect on the limit. Take a look at this one. As I approach from the left side, what value is my graph approaching? 2. As I approach 1 from the right side, what value is it approaching? 2. Did it get to 2? Yeah, but it's irrelevant. It's totally irrelevant. It's where is it intending on going? Are they approaching the same value from either side? Okay? So in each of these, the limit of f of x, the limit of g of x, and the limit of h of x is all 2. Okay? All right. Yeah.
What would happen if there was approaching from 2 different numbers?
Then the limit would not exist. Dean, remember? Yeah. I know. Okay. So, let's talk about some properties of limits. What happens if you have the limit as x approaches c of a value k, right? So for example, look at this example here. The limit as x approaches 2 of 3. The function is this one. This is the function. This is the function y equals 3. Okay? Let's graph y equals 3. It looks like that, right? Now, it says the limit as we're approaching 2. As I'm approaching 2, what value is the y approaching? 3. As I'm approaching 2 from the left side, what value is the y approaching? 3. So when you have the limit of a constant, when the function is just a constant, it's just 3 all the time. It's just a constant all the time. Now, what if the function that you're finding the limit of is y equals x? We call this the identity function. Right? Remember you have a quadratic function, this is an identity function, y equals x. Okay? So, if you have y equals x, okay, as you approach 3 from the left side, what value is your y approaching? 3. What about from the right side? 3. So it's basically the same as that number when it's the identity function. Okay? So what happened? It's as if we just plugged in 3 into the x. We just substituted 3 for x. Okay. These are all of these rules that we put there. We don't ask you to memorize. We're going to use them as we, as we go through the section. So I'm not going to ask you guys to memorize any of those. So let's do the first one there. You have the limit as x approaches 2 of pi. What kind of a function is pi? What is pi? It's a constant, so it's going to be just pi. Okay? No. Pi. Okay? Yeah. Guys, let's focus here. Yeah.
How would you know that it's just pi? I know it's a constant, but how would you know it's a constant?
Pi is just a constant. I mean, it's never anything but the pi that you know.
So was 3 up here also?
Yes.
How would you know that 3 was a constant?
Constants are basically just numbers. So it could be 1, 2, 3, 5, 700. It could be pi. It could be root 4, root 3, root 5. Okay?
So it will always be whatever this is, like limit, whatever that is for now, will be the answer. Whatever it says after.
For this particular problem. Yeah, not for the next one. Okay. So for the next one, we actually have a function, right? So what are we going to do here? We're going to take a, the limit as x approaches a, and we're going to plug it into our variables. Okay? So this is going to be 2a squared minus 5a plus 3. So if it was this, the limit of this function as x approaches negative 7, we just plug negative 7 into x, and that's it. Okay? And then, of course, we simplify. Okay. This is why we spent so much time last year. Okay.
Is that the answer?
Yeah.
You don't need to simplify it anymore?
It doesn't simplify anymore.
You can't go factor or
No. So here, what are we finding the limit of? If the thing that you're finding the limit of is a polynomial and a rational function, okay? If the thing you're finding a limit of is a polynomial function, you just plug in the value. That's it. Just plug it into all the variables. Okay? So we just plug in x equals 2, and I get 2 squared plus 3 times 2 minus 4 That's a 6. Okay? Now, what if I have a rational function, like a fraction? Well, I have a function on top. I have a function on the bottom. So I just plug in c at the top. I plug in c at the bottom. The one thing you have to watch out for, you just plug in the value. Again, just like we did up there. The only thing you have to watch out for, though, is that by plugging in c in the bottom, the denominator is not going to be 0. Okay? So, like in this case, if you plug in the 2 or the negative 2, you don't get a 0. And then we'll talk about what happens if you are going to get a 0. So in this case, it's just going to be negative 2 plus 1 over negative 2 squared. And please let's not forget the units, the parentheses there. So negative 1 over 4. Okay? You can just leave it like that. Okay? Here, right? Same situation. So it's going to be 2 cubed minus 2 times 2, 4. I'll talk about graphically in a minute. Here, we're going to plug in a 1. So it's 2 minus 7 plus 4 plus 5 all over 3 plus 2. 3 plus 1. I'm plugging in x equals 1 to all of the x's.
So, yeah.
Yeah?
Because I was thinking it was to the third. Like
Oh, yeah, right.
But it was just 1.
Mm-hmm. Yeah.
What happens if you plug it in and it says the denominator will equal 0?
That's a whole other process, which I've purposely given you ones that don't go to 0. So here are some rational functions. We're going to plug them in. 2 into t, we get 2 squared minus 3 minus whatever. What do you get? What do you get on the bottom? 0. That's not cool. So now to answer your question, what happens? Well, we're going to have to simplify. This is the limit as t approaches 2 of, let's factor the top, t minus 2, t minus 1. The bottom, t minus 2, t plus 2. Yeah, the t minus 2's go away. The limit as t approaches 2 now of t minus 1 over t plus 2. Okay, so that we could totally do. And that's just 2 minus 1 over 2 plus 2, 1 over 4. Okay, so when it says when it says determine graphically or support graphically, all it asks you to do is to put it in the calculator, graph it, and visually see what the limit is. Okay? Now, here's a little bit of notation for you. This limit symbol has to be carried throughout the problem until you get to the point where you're physically putting in your value. And it will be points off if you don't carry it because it's just wrong. Huh? It should be here, not here, because here I actually plugged in the 2. So as long as you have variables, you have to have the limits. Okay? You don't put them when you don't have your variables. Okay, here, when I plug in x equals 0, I'm going to get something divided by 0, which is not cool. So I need to simplify a little bit. So here's all your past algebra skills now, algebra 1 and algebra 2, that are going to come into play. We're going to have to do a common denominator on top there. So what will be the denominator? 2 plus x times 2. 2 times 2 plus x. All right, because you have a 2 plus x and you have a 2. Okay? So on the top, we're going to get, right? On the top, we're going to get a 2 plus x minus, what are we going to get on the top? It's going to be 2 minus 2 plus x. Okay? All right. So basically, look at this first denominator and the common denominator. And if you compare them, what's left over? Like what's different? The 2, right? The 2 plus x and this, the 2. So it's 2 times 1 minus, if you compare these, the 2 plus x is left over times that 2 plus x. If you have questions on that, come to bonus. We can go through some of that algebra business. Okay, so what do we have here? We have the limit as x approaches 0. So let's see. I'm going to distribute the negative. It's going to be 2 minus x. So it's going to be negative x. Is that right? Okay, so now, whoops, I already fell into my own trap here. So limit x approaches 0. Okay, so limit x approaches 0. Now I have a fraction divided by x. So this is like the fraction times 1 over x. Okay? Cancel out the x, cancel out the x. What do I have left? Limit as x approaches 0, negative 1 over 2, 2 plus x. Okay, yeah. You don't have to, because now we're going to plug in our x equals 0. Now it's safe to do that. So when I plug in the x equals 0, I get negative 1 over 2 times 2. I can drop the limit, okay, and I get negative 1 over 4.
Why did you multiply it by 1 over x?
Because it was that fraction divided by x. Okay. So lots of algebra, but unfortunately, like it's part of the process. So this next thing you guys did last year as well. Remember when we were doing like left-handed and right-sided limit? Yeah. So right hand. If you look at the x-axis, the right hand is where the values are all positive. The left hand is where all the values are negative. So right hand, it's denoted like this. So it says the limit as x approaches c plus from the positive side. And it says x approaches c from the right. The left hand is as x approaches c from the left. And it's limit as x approaches c minus. And the big thing is, if you look at the limit from the right, and let's say from the right it's approaching a value of 2. If you look at the limit from the left, and let's say it's also approaching 2, then the limit of the function at x equals 2 exists. Okay, all words, let's do a tangible problem. Okay. Evaluate the limit. So the limit of f of x as x approaches 0 from the left. So as x approaches 0 here, what value? It's approaching 5. As I'm approaching the limit as x approaches 0 from the plus side, what value is it approaching? 5. Because these are the same, so at x equals 0, it's also 5. By the way, what if I were to ask you as like part C.1 or whatever, right? What if I were to ask you what's f of 0? What would you say? I would say 5 too, right? So f of 0 is equal to 5. That's the actual value there. All right. So what about the limit as x approaches 3, a negative 3 from the negative side? Negative 3 from the negative side is 0. Negative 3 from the positive side? Sorry, 5. Yes, no, 5. You're right. I'm sorry. I was looking. 5. Right. Because here, yeah, so as I'm approaching the c equals negative 3 from the right side, if I'm here, I look up at the graph and it's here. And as I'm approaching this negative 3, the value of the graph is approaching 5. Okay?
Oh, I didn't look at the one above.
Right. So now, because these are not the same, this is d and e. By the way, what's f of negative 3?
It's 2.
F of negative 3 is 2. This is the actual value, has nothing to do with the limit. Okay, let me say one more thing, and then we're going to do the next part next time. But let me say one more thing. As far as homework is concerned, it will be due Wednesday.
Where is the homework?